in front of a, if it's present in front of a, a cold cloud, then it can give rise to the absorption lines. So it is a backdrop for absorption line spectrum also. So the second one is regarding so second law is regarding the emission line and states that a hot transparent gas, it produces a emission line spectrum. So an example for emission line spectrum is the spectral emission lines coming from the outer atmosphere of sun, the corona. You will learn more about corona in the coming sessions. You will be having complete lectures on the atmosphere of the sun, so you will learn about them. But the corona satisfy the condition stated by this law, and we obtain emission line profile, which comes from the corona. Even chromosphere of the sun, you can see many emission lines from there. Then the third law, it states that a cool transparent gas, so and a dilute gas, which is in front of a source which is giving a continuous spectrum, it produces an absorption line spectrum. So example is the light coming from the photosphere of sun. So as I told you that the light coming from the interior of the sun is of continuous, means it's the spectra of that line is in the form of continuous spectra. But since the photosphere is cooler than the interior of the star, and it is satisfying these conditions for most of the lines, so you will get this kind of a continuous spectra along with the these black gaps which are being absorbed by the photosphere. So these last two spectrums, they are the line spectrums, emission line spectrum and absorption line spectrum, and we will be working on a line spectrum in this project. So in astronomy, the shape of a spectra is determined by many factors. Okay, I'm talking with respect to line spectra. Okay, the shape of a line spectra can be determined with many physical factors like temperature, the collisions, and unresolved motion with respect to the object that you are observing. Means what's these things, I mean these parameters, what are the parameters in the environment that you are observing. So we will learn more about this line shape in this project, and which you can also call line broadening. So you will learn about line broadening mechanism in this project. And the shape, a spectral line, it is characterized by some important parameters like the peak intensity. Okay, pointer. Okay, the arrows are pointing, it's not working that way. So peak intensity and the line width and the central position of the line. Okay, so what we will do in this project, so you will be given a spectra, and luckily it's a simulated spectra, it's free from noise. It's simulated spectra of coronal emission line, so iron 13. And what you have to do is that you have to do spectral line fitting, Gaussian fitting over this data, this spectra, and then you have to obtain parameters like mean, standard deviation, and centroid, and they will be helpful in finding total intensity, Doppler shift, and line widths. And you will learn that how you can find it. It's quite easy, and if time permits, then we can, so this data set is very easy. You will only get a single spectra, but if time permits, we can work on a more complicated data set which have multiple spectra that I can discuss with you while we'll do this project. And we will work in Python, and I will prefer the use of Jupyter Notebook for this project. And I think I have mentioned about the group members. So that's all what we will do in this project, and I'll see you during the sessions. Thank you. You can show the group members again. Oh, yes. Yeah, I'll. So my team members are Krista, Shakti, Shribala, and Deepa.
Someone is already here. Next presentation is by Arpit. So it's on exploring the connection to observing.
So, hello everyone. My name is Arpit K Shrivastav. I'm a PhD student here, and this project is about exploring the Sun-Earth connection through observation. I will guide you through. I will guide you for 10 days through this project, and one other mentor also will come for you. Click करना होगा. So Prateek will join in the middle of this workshop, and he will also guide you a few things about this project. Okay, so we will let's see what sun-earth connection is. So sun-earth connection is mainly driven by space weather, which refers to variable state of the coupled space environment related to changing conditions due to the sun and its effect on terrestrial atmosphere. So there is some changes. There are some changes in sun's magnetic field, and these changes are seen in the on the Earth in the variability of magnetic field near around the Earth. And these effects can be seen at Earth at different like different phenomena, and there can be auroras in the northern part of Earth. It can affect our satellites. It can affect our communication. It can affect our electric power. Through satellite, it can affect our GPS. So, I mean, it has a lot of effects which we need to know. Which I mean, we need to know how space weather is behaving right now, so that we can mitigate these effects. Okay. So what are the main space weather drivers? So on the sun surface, we see solar flares. It can be seen in multi-wavelength, and solar flare are one of the highly energetic phenomena which can appear on the sun surface, and it can affect Earth as well. Other is CMEs, coronal mass ejections, which will be they are outward. There are plasma material going outward from the sun in the form of CMEs, and they can affect Earth as well. Others are space driver solar wind, which are highly, these are energetic particles which are coming constantly from the sun, and they interact with Earth's magnetic field, and they can affect as well, because we also see auroras. They can also be a consequence of these space field drivers. So in this project, we will study event which happened around 3rd February, and it affected around 40 satellites of Starlink. You know about Starlink or not? Yes. So it affected 40 satellites of Starlinks. It damaged it, and we will see how a space weather driver can damage the satellites in our Earth's atmosphere. So this news came around 3rd February, and they found that a geomagnetic storm happened, and it killed around 40 new space satellites. So we will try to find out not the cause. We will try to study the properties of this space, the space driver of this particular event, and we will try to find out how this happened. Okay. So what are the observation we are going to use? We will be using near Earth observation from HDO and X-ray. We will use X-ray flux from GOES, and then we will also try to see how CME looks, the particular CME also that happened due to which geomagnetic storms happened. How it look in white light images, which we will do from SOHO and stereo, and we will. Work nahi kar raha. Yeah, we will also try to measure the strength of the storm by in situ measurements, which will be at L1 point from S. So we will try to. This is not a project in which you will go deeper into data analysis. It will be a general project which will guide you to what are the things can happen in space weather and how we see them, how we analyze them. So the team which will be working with me doing this hard work, okay, will be this. These are the the members. Okay. So if you want to know more about the project, you can scan this. Okay, and the participant who will be working with me, scan this and get a more detailed PDF about this project, what we'll be going to do. Okay, so thank you for your attention.
Arpit is also covering for other two mentors for today, and then he will be presenting on behalf of other students. So the mentor for this will be Nitin Vashishtha. This project with your characterizing CMEs will be able to your
देख नहीं पा रहा हूँ मैं क्या है। ठीक है हेलो स्लाइड्स Okay, so Nitin and Jyoti are not here. They are PhD students in Aries, and they will be guiding some of you about the characterizing CMEs in inner corona using JHelioviewer. Okay, so let's see what I mean. The CMEs are. So CMEs, the full name is coronal mass ejection, and these are observable change in coronal structure that occurs on a time scale between few minutes to several hours, and it involves, I mean, there is outward propagation of bright white light features. In this is a coronagraph. I mean, these you will able to know about coronagraph in later lectures, but these are mostly seen in coronagraph images because the disk is more bright and we block that. Okay, so CME is has been seen to be typical three-part structures, which is leading edge, cavity, and bright core, which has been shown by these arrows. And we to know what is the position of CMEs in particular coronagraph images, we defined a center position angle, which is called CPA, and it is measured from solar north. And suppose and there are other parameters related to the CMEs, which are width of the CMEs, which we measure like this. What is the extent in the coronographic field of view of the particular CME? Okay, and we track we can track CME to get the property to get familiarized with the properties of what is the time distance, what is the velocity of particular CME at the time progresses, what is the acceleration of particular CME, that we can measure by these chronographic images. And this is a particular high time plot for one CME, and the velocity is also quoted in the bottom of the image. And they have also measured velocity height graph, and we can do that using these coronographic images. Okay, and what if a CME is directed towards the Earth? It will be fun in the space. We will think like that, but not. I don't think. So these are the particular. ये पट्टी हट सकती है क्या ऊपर जो है? ठीक है. So these are the instruments which observe the sun, either in situ observation, whether in the remote sensing observation. These are the spacecraft which lie between sun and earth, and you guys will mostly use. You guys will mostly use stereo data. Okay, so stereo, you can see the image of a CME. I mean this video in which CME is going outwards, and this 1.5 R0 is the inner corona. I mean which is I mean the stereo has a, I mean the field of view from after 1.5, I think. So what will the objective of your project? You have to understand different imaging observation of the solar corona, then learn to use the JHelioviewer software for different instrument, and then you have to track and characterize the CMEs using JHelioviewer. Okay. So this JHelioviewer particular tool or software, I can say, you have to use, and you can access the datasets from different servers in this tool, and there are a lot of functionalities in this tool which you can explore later in the project as well. Okay, and so this is the what you can say, the path of the project. You have to learn the JHelioviewer interface, play around with different buttons. I mean, play around with whatever functionalities that are given there, load the required data, characterize the CMEs, and then you are ready to analyze everything. What will be the team for these two mentors? The first team will be with Nitin, and these are the team members. Okay, and the second team will be with Jyoti. These are the team members with Jyoti. Okay, please note that, and thank you for the listening to this. Yeah.
Okay, if all of you have noted, maybe the next speaker.
So the project to be done by me is the Sunspot Classification using DBSCAN, and this is the contents of my talk. And so first, let us know what is the sunspot from the title itself. So when you see the sun in general, we don't see much interesting features like this. You can see there nothing much interesting thing. Okay, it's boring, but when you see some particular days, we see this here you can see the dark features. Those are called the sunspots. Yeah. So here you can see this sunspots are the dark magnetic features because they are dark, because they are cooler than the background of the photosphere. And when you see this sunspot in a large zoom version, we see the two structure of the sunspot. This dark portion is called the umbra, and this less dark portion called the penumbra. And this sunspot is also the magnetic features, as I mentioned, and these are in generally bipolar in nature. Like here you can see these magnetic field lines. These are two polarities of the sunspot. So in generally they are bipolar in nature. These sunspots have been observed for large number of years. And here you can see this 400 years of sunspot observation. After that also there are sunspot observation are there. And this peak is called the solar maxima, where the number of sunspots are maximum. And the minima, this point you can see is called the solar minima, where the number of sunspots are minimum. So these sunspots follow the periodicity of around 11 years, not exactly 11 years. It can vary 10.9, 11.2, but approximately it's 11 years. So this is called the solar cycle. So you'll know more about this solar cycle and all in the later lectures in this workshop. So these sunspots actually are classified based on their size, complexity, and magnetic properties. And this actually, change हो गया इसका. Actually, this is a Macintosh. जो लिखा है ऊपर ये Macintosh है. इसके इसमें font change हो गया. Sorry. So this is a standard Macintosh sunspot group classification. So there are A type, B type, C, D, E, F, H. A type is actually sunspots that those show bipolarity, don't show bipolarity. Also, they don't exhibit penumbra. Like here you can see, penumbra is not there. And in B type, they show bipolarity, but they don't exhibit penumbra. And in C type, they show they show bipolarity, but either the leading sunspot they show only penumbra. And in D type, both lead and trailing means lead means this is called leading sunspot, and this back here you can see it's called a trailing sunspot. So they in D type they both show penumbra. And in E type, actually, it spreads more in longitude, like 10 to 15 degree longitude. And F type are called more extensive sunspots. They cover mostly in excess of 15 degree longitude. And in H type is called the decaying, when sunspots are decaying, those classifications. So in the project, you will know more about this classification and all. So basically in this project, we'll use the data of SDO-HMI data. This is SDO-HMI image, intensity continuum image. So this SDO is Solar Dynamic Observatory, which was launched by NASA in 2010. And the SDO has many instruments. One instrument is HMI, helioseismic and magnetic imager. And this HMI looks at the photosphere of the sun. So here is the very famous meme of the machine learning. So basically in this project we will use the machine learning algorithm, because in solar data we have large number of data sets. Okay, so mostly in machine learning has been used in so many fields. In solar physics also we are using machine learning techniques, because we have specifically we're talking about the sunspot classification. We have large number of data set, like from 1875 we have RGO data, and we have in Kodaikanal Solar Observatory also we have 100 years of data. So to classify these sunspots manually, it's very difficult, and it may cause human error also. So by using this machine learning techniques, we can actually classify automatically. So in this project, we will be using this DBSCAN technique, and this is actually one of the unsupervised machine learning technique. There are different machine learning techniques, but this is one of them, and this is mostly very efficient for the clustering of the sunspot. So here you can see this is the basic means understanding of the DBSCAN. From the name itself, you can understand that density-based, spatially clustering of application with noise. Density means it's mostly deal with the dense data sets, clusters, and spatial clustering means you can understand that it takes the values of the spatial positions of the data sets. And also it tells about the application with noise, means it deals with noise also. So here you can see if there are many data points. So these red points are called the core point. So basically in DBSCAN, there are two key parameters, EPS and minimum points. So EPS is actually the distance that specify the neighborhood. Means like here you can see the distance between these 2 points are defined by the EPS, and the minimum points is the minimum number of data points to define a cluster. Means we can give 4, 5 to define a cluster. So these two parameters are crucial to for the DBSCAN algorithm. So these are called the core point, where we define the cluster. Means it's within this minimum distance EPS, and if it's lies within the border, then it's called the border point. And this blue point is called the outlier. It's actually when you define the EPS, if it is greater than the EPS or greater than the minimum points, then it considers as a noise. Okay. So you will understand more about during the project, because it's so many other things also there. I cannot cover in this presentation. So thank you. And these are the group members: Arjun, Nagasri, and Sambit and Nutan. I think after these we can catch up. Thank you.
Okay, our next speaker is Srinjana. He will be speaking on detection of chromospheric plages in small units.
Okay. Pointer. Okay. Thank you. तो है उल्टा क्यों जा रहा है? उल्टा जा रहा है नीचे वाला. अच्छा. Okay, so good afternoon, everyone. I am Srinjana. So I'm Srinjana. I am in the second year. Hello. Okay, so let's restart. I am Srinjana. I am in the second year of my PhD, and being one of the mentors attached with the 4th Aditya-L1 workshop that is being held today here at Aries till 7th of July. I'll be giving a peek into the project that I will be walking you through. That's concerning the detection of chromospheric plages in the solar atmosphere using SDO AIA images. Now I've used a lot of jargons over here. Before we go on into the what, why, and how, let's first look into a brief overview about the solar atmosphere. So starting with the coolest and the densest layer of the solar atmosphere, the photosphere, which we commonly term as the visible layer of the sun. The photosphere has the temperature of the orders of 10 raised to 3 Kelvin and is the thinnest layer of the solar atmosphere. The most common features visible in photosphere are the sunspots, as was discussed by Dibya. Some of you will be working on that project. But as we move on from the photosphere to the chromosphere is much more thicker, and we see a temperature up to order of 10 raised to 4 in this particular layer. The chromosphere derives its name from the Greek word chromos, which means color, as you might have seen in some of the solar eclipse images, some red extended feature on the solar limb. So that's the H-alpha line that you see. So chromosphere is visible in different spectral lines like the H-alpha. Then there is the calcium 2K. There is also another line, 1600 angstrom, which we will be seeing. Now from the chromosphere, we have the transition region, and the transition region is the thinnest part of the solar atmosphere, only about 100 kilometers thick. But through the transition region into the solar corona, which is the sparsest layer of the solar atmosphere, we see a rise of temperature of the temperature to an order of 10 raised to 6 Kelvin. Now that we know that, let's look into our specific project. So we will be dealing with images of the chromosphere in 1600 angstrom. So this line sees primary contribution from the C4 ion, and this is sensitive to a temperature of about 10 raised to 5 Kelvin. That's 1 lakh Kelvin over there. And since we're looking into the chromosphere, that's the higher solar atmosphere, the magnetic field effects are pretty dominant. So this is a high beta plasma. So on the right-hand side of the image, you can see that there are several things happening over here. So you see that there are some bright features over here. These are the part of the chromospheric model network and are also called the network bright points. Now the congregation of these bright regions that you see over here, these are the plages or the chromospheric faculae. So now that we have come across the name, what exactly are these plages? So these plages or the chromospheric faculae they derive their name from the Latin word for faculae, which means little torches. So these are areas, extended structures above sunspots. Like in this image that you can see, this small area is a sunspot, and this entire extended region in the chromosphere is a plage. So these are regions of very strong magnetic flux, dense magnetic flux. So there is strong magnetic field of about 100 Gauss over here. And this stronger magnetic field leads to lesser absorption of certain lines like calcium 2K. And this leads to the brighter appearance of the plages. So why are we interested in plages? Now, since I already told you that plages are magnetic structures, so that means they're very related to the solar magnetic field. So if we are able to look at the plages separately, their evolution and development with the solar magnetic cycle, we might be able to get a peek into how the sun's magnetic field is evolving, forming, changing. So that would lead us to better understanding of the sun. So now that we know what we are working with, let's first look at how the data source and what the data is. So the Solar Dynamic Observatory has atop it the Atmospheric Imaging Assembly, which is a congregation of 4 telescopes. And these telescopes have 10 wavelength channels, and all these wavelength channels takes data in very high cadence and also in very high spatial resolution. For this small project, we will be using data from only one UV channel, 1600 angstrom, no surprise over here. And this data is from the period of August 2014 and is at the intervals of 6 hours. This data is already level 1.5, so you don't need to do the pre-processing and all of that for image registration and plate scale alignment. So we will be using this level 1.5 data only. So now that we have the data, let's look at how exactly we are going to approach this problem. So for any image, we know that each pixel has a specific value, which we call the intensity, right? So if we plot the intensity histogram of a particular exemplary image, we see that all of these pixels are distributed in certain values of intensity beams, right? So according to this intensity histogram, we can divide any image into 2 specific classes, like the regions of interest, which is the plages over here in our case, and the background, whatever we do not care about. So once we have these 2 main classes, let us remember that plages are brighter. So there is significant intensity difference between the plages and the background. So we will utilize this fact over here. And what we will do, we will set an intensity threshold on the image, which is based on the mean intensity value of the entire image. So if the plages are significantly brighter, so it will obviously lie on the higher side, though all the pixels belonging to the plages. So that's what we are going to use, and we were going to demarcate all of those pixels as 1 and all pixels other than that as 0. So let us now look at the roadmap of the journey that we are going to undertake. But like any other journey that we take, there are certain prerequisites. Like for any train journey you take, you book the tickets beforehand, right? So the prerequisites over there would be that you are required to have some basic knowledge in Python and are required to have Python installed or some form of environment installed in your devices. So if it's better if you have higher versions of Python, not 3.11 obviously. But yeah, so once we have that out of our way, we will start with this image. We will subject it to some pre-processing, that is, we'll remove the noise and everything, and then we'll subject it to the intensity thresholding that we talked about. And then voila, we should have this kind of binary map of the plages. So that is done. Now, let me call out my team members who will be these 4. And guys, if you see your name over here, please kindly scan this QR code. This will take you to a Google Drive link where you will have all the essentials that you need for this 9-day project. And I'll give you some time for all of you to do that. And if you're done, then thank you. Oh, okay, you're okay. Scanner, the scanner there.
Okay, let's start with
Hello everyone, I'm Upasna Baweja and we will be doing project on coronal seismology of solar coronal lobes. So I think many of you are familiar with the word seismology, right? So any idea what is it? Anyone? So if we go through the Wikipedia definition of seismology, I can change slide here. So if we go with the Wikipedia definition of seismology, that is a scientific study of earthquake and the propagation of elastic waves through Earth or any other planetary body, right? So as we know that there are different types of waves when we want to study these seismology. So these are body waves, surface waves, and normal waves. But why do we want to discuss about these waves? So is there any question in your mind, like why we want to study these waves? How will they help us? So basically, the benefit of studying these waves is they can give us information about the medium in which they propagate. So in this case, that is the Earth's interior. And also it can help us provide information of the center of that earthquake. So if we go on the similar lines and we study the waves in the solar corona, so that will help us to understand the properties of the solar corona or solar atmosphere. So we will use the MHD waves in the solar atmosphere, and for that we will be using the data from AIA. AIA is Atmospheric Imaging Assembly, that is onboard solar dynamic observatory. So this was launched by NASA in 2010. So we'll be using this data and we will try to derive or estimate the coronal properties using this data. So we'll be using the this data to estimate the magnetic field in the solar atmosphere. So this is all about our project, and project students are Anurag, Meenakshi, Sachit, Akshay, and Meenakshi. Do Meenakshi. So
let's try and start there.
नहीं नहीं ये no here first one is going like this no and then okay no okay myself Balveer Singh. I am here postdoctoral fellow under the Aditya-L1 support cell, and I will do the project with some group members Amrit Datta, Kartik Richa Yadav, Suraj and Himani Mehta on MSD, various MSD waves, which is the energy transport phenomena in the solar atmosphere using the PLUTO code. So basically why we do MSD and how to do MSD. So here I am talking about what are the MSD model. So basically we are using in MSD model of the single particle. It means only one type of particles present in the simulation box, which I consider the hydrogen ions H+, and it is basically a approximation which deals the various kinds of waves as well as the transients phenomena in the solar atmosphere. So the MSD modeling, so the perturbations of various background plasma, like background physical plasma, like magnetic field, plasma velocity, and mass density, which is described in the single fluid approximation. And we solve basically the set of MSD equations in both the ideal regime as well as the non-ideal regime. So we simplify the equations of fluids equations as well as the Maxwell equations. So why to study the MSD? So MSD is the approximation to crucial to describe the various transients as well as the waves phenomena in the solar atmosphere. And you know already waves as well as the transients phenomena is the most prominent phenomena in the solar atmosphere, which take account into the transporting of the mass as well as the energy into the upper atmosphere from the lower atmosphere. So these MSD approximations is describe the evolution of various type of waves, which I will discuss in the later in detail. Type of alpine waves, MSD slow waves, and fast MSD waves, and the transfer of plasma energy and momentum, which is the localized coronal heating problem, as well as the mass flow, which may be cause of the acceleration of the solar wind. So these are the some interesting things which occurs in the solar atmosphere, coupling of the various atmospheric layer. And also this is basically it is very simple way to describe the various phenomena as compared to the like other phenomena like a kinetic theory as well as two fluid models and multi-fluid models in the solar atmosphere. So these are the set of MSD equations. So slide is not moving. No. Here slide is moving, but yeah. Okay. Yeah, okay. So here not change. Okay. Maybe. Maybe.
dash L capital
capital A.
T capital
Uh,
dash L capital.
L1. Okay, so these are the set of the ideal MSD equations which will be solved by using some initial conditions like what are the density profile, what are the pressure profile, temperature profile, and magnetic field, and all the parameters which will set in the background parameters, and some interesting things, the boundary conditions. So we will apply the boundary conditions when we start the project of the various waves of the solar atmosphere. So these set of equations, the first equations we know the continuity equations, which is the based principle of the conservation of mass, and second equation is the momentum equation. Third one is the induction equations, which is based on the principle of the conservation of charge, and fourth one is the energy equations, which is based on the principle of energy, and for last equation is called the ideal gas equation. So these MSD equations used to solve the our problem, like transportation of waves, MSD waves and alpine waves in the solar atmosphere using the some initial conditions as well as the boundary conditions. So here, okay, slide is not changing. Okay. So here, for your kind information, we set the initial configuration of magnetic field lines, where the magnetic field lines is smoothly extended behavior, showing in the solar atmosphere up to the 0 to 20 megameter. We can set according to our problems, and we will make the different geometry of the magnetic field lines, like curve magnetic field lines, null point geometry, according to our problems. And these are the temperature profiles. So we can see here the temperature going to lowest temperature just below the chromospheric layer, that is 2.7 megameter in this model, and the temperature is abruptly rise in the transition region up to 10,000 Kelvin to 1 mega Kelvin. So these are the initial configuration which we'll discuss in detail when we start the project. Okay, and these are the also background some parameters. How can we set in the MSD modulation? So this is the first one. This shows the magnetic field geometry, and this is the plasma beta extension. How the this is the plasma pressure and mass density profile in the solar atmosphere, which will set in the MSD simulation. And these two are the alpine velocity and sound velocity profile in the solar atmosphere. So basically, when we start, so we will discuss in details. And these are some interesting results which I have done already in my PhD. So okay, so we still facing her. So these are the some interesting problem which I have done in my PhD. So you can see here the null point geometry magnetic field is showing here, and there are some oscillation present in the these jet-like phenomena, which I will discuss in later when we will start the project. And you can see here the cool loose formation, cool jets. Why you say cool jets, we will discuss in later when we start the project. And these are the some specule-like just plasma flow at the null points. So all the things when we modulate and start the project, so we will discuss. And you can see here there are some transients, cool jet-like phenomena. So due to weak internet connection, there are some problem, but yeah, okay. So when we start the project, so we can see all the things and related all the phenomena, or how can solve the problem using the set of MSD equations. So you can see here, because internet connection is very unstable showing, and this movie shows basically the generation of various type of jets, which is associated with the various MSD waves, which we will done in the project. So these are some MSD, these are some specule-like jets and cool jets, which is associated with some plasma processes, which we'll discuss in the when we start the project in detail. Okay, so so again we remind the reminder about the our group: Amrit Datta, sorry, Karthik, Richa Yadav, Suraj, Himani Mehta. Okay, so thank you so much for your kind attention.
Okay, I'll also note down our next speaker is Anmo. So we'll be speaking on solar physics detection using AI-based computer models. In the meanwhile, as you can see, I think most of the projects are required for you to have a laptop or some sort of device where you can do the project. You can install software, you have rights to install software and all. So I suppose Anmoy has already mentioned this to you. So in case some of you don't have laptops, then you have to organize among invest yourself in different ways accordingly. If none of you in the group have laptops, then that can be a problem. So I suppose most of you bring your own laptop.
Open. Okay, ये select करना पड़ेगा. Share. अच्छा, शेयर ऑलरेडी हो गया है. हाँ, देखिए. उसको हाइड कर. Okay, good afternoon all. My name is Sonmoy Bandyopadhyay. I am Senior Project Associate here under Aditya-L1 Support Cell project, and my project is mainly on the development of AI-based computer vision algorithm and for analysis of solar images actually. So I think most of you already familiar with the term AI, with the familiar with the AI, right? Yes, because the famous ChatGPT is already based on your AI. So I think I don't need to explain about the AI, but there are different algorithms are there which are exist in the domain of AI. And mainly my work actually focused on the development of fuzzy-based algorithms, which is something deals with the uncertainty or where there is some ambiguity is there. That thing handles that fuzzy-based AI handle these sorts of things. Okay, so my Actually, this project which we'll do in the next few days, actually, it is totally my PhD work, where I mainly focused on development of AI-based computer vision algorithm for this detection of this solar coronal hole. So, frankly speaking, I am not the good physicist like you, but my main focus on the development of computational science or computer based algorithms. So, but till I am giving some small introduction that actually this coming. Okay. So this solar coronal is nothing but some dark areas observed as dark area on this solar corona, and it is mainly observed in the solar EUV, that is extreme ultraviolet images and X-ray images. And these regions are become more apparent corresponding to their other region because they are much cooler and less thick segment than the encompassing or the surrounding plasmas. And why I was interested in this because these solar coronal holes are has some huge influence in the generation of the solar wind, and as well as it has some variation in the space weather. So if we can detect this solar coronal hole region properly, so then we can have the better prediction about the space weather condition. So I think Arpit has giving this introduction about this image, so I am not spending time on this. So there are different solar observatories actually. These are some ground-based and these are some space-based solar observatory. So I have used the space-based solar dynamic observatory data for analysis or detecting the solar coronal hole region because of the two things. At very first, I told you that the this solar coronal hole can be observed in the extreme ultraviolet images. So these extreme ultraviolet images can only be accessed through the space-based solar observatory because our Earth ozone layer actually stops these ultraviolet rays, and which is difficult for capturing those ultraviolet images. And now, among these existing solar space-based solar observatory, why I'm focusing on this SDO-based images, because these SDO-based images having the high resolution compared to the other solar images captured by other space-based solar observatory. So therefore, I have focused or use these SDO-based images, and for detection of these solar coronal hole region, mainly three images are quite useful. That is 170 SDO AI images having 171 Armstrong, 193 Armstrong image, and 211 Armstrong image. So these three images are quite good, or actually fit quite well for detection of this solar coronal holes region. So this is what actually look like. This is the original solar image. If we try to plot on any system, actually I have used your MATLAB software, because it is MATLAB means your matrix laboratory, and the image which we will deal is nothing but the arrangement of some matrix with having certain intensity levels. Okay, so that the matrix element is nothing but the pixel intensity level. Okay, so and MATLAB is quite good for these handling these matrix and matrix data, but unfortunately that is not the free software. So whatever in the next coming days we'll do all these things using your Python software. Okay, so which is available freely online. And this is the enhanced image, this bright region, and this is the colorized image. And but don't think that this is the actual image, but this is nothing but a false color image, actually. False color image of these solar UV images. Okay, so actually till now, what happened? Till now, the NOAA at Space Weather Prediction Center till now detect this coronal hole region using classify this region through the handmade images. You can see this is nothing but your hand-drawn images of this same coronal holes. But what happened with the development of the instrument or space-based solar observatory? So different type, the data which are coming near us is quite large, quite large. Actually, it is quite big in volumes. So drawing the coronal hole every time in using your pen and pencil is quite difficult. So therefore we need to shift in the automatic detection algorithm or automatic computer vision algorithm. So, but till now, what happened? Till now, none of the existing automatic computer vision algorithms stand suitable so that it can be used for this detection. But till we are those or any computer vision algorithm till now stand so much suitable, there is some less or chance of errors in detecting, which I will show you later. So for my case, I have developed one algorithm. It is contour-based algorithm. So actually, it is not changing. Yes. So this is the contour-based algorithm. This is also a AI-based computer vision algorithm. Actually, it worked like your principle of physics. Actually, when you have some elastic, have you seen? You all have seen the elastic rubber band, right? So what happened? On the side of some object, if you release the elastic rubber band, it will get stuck on the boundary of that object. Okay, so same principle is been followed here. So when we generalize the contour around this around the boundary of the images, it gets stuck on the object of interest or on the boundary of object of interest. So same principle has been followed here, and this is the actual procedure. So what happened here? These are the two images. This is the mask, that is the black and white image of the sun, actually. So a contour is generated on the boundary of the sun or on the solar boundary. Why it has been generated on the solar boundary? Because the main advantage is that while searching the coronal hole boundary, it will take less region as compared if we generate this boundary near the image boundary, this contour near the image boundary. Okay. Next, what happened? Next, I have cleared out this region, that is non-solar region. Why? Because whenever I release the contour around the boundary, wherever it gets strong edges, it gets stuck on that, and it will not reach the solar contour, solar coronal hole boundary. So therefore, I have removed the region outside this initial contour. And next, based on some formulation, what I have done this contours to move towards this solar coronal hole region, and ultimately this is the main result which has been detected. So these are the some results. which has been detected using different AI-based algorithms. Like, and here 2 algorithms has been used to generate the contour. One is circular Hawk transform, which has been developed by Duda and Hart to detect the circular object in the images. And some fuzzy-based algorithm are also there. So these are some final result, and some unwanted or redundant region has also been detected as the coronal hole region, but that is not our region of interest. So what happened, we here use some filter like image morphological operation to filter out these redundant region and to keep the region of interest in the images. And these are the coronal hole which has been detected. Okay, so if we can see, actually what we want when we develop some algorithm, we want that it should give some 100% accuracy. Okay, but unfortunately in our case, none of the algorithm has reached the 100% accuracy of detecting this coronal hole. But till you can see this region has little bit higher accuracy compared to the other existing algorithms. Okay, so therefore now our focus is to develop this algorithm further so that it can achieve not 100%. It is not possible for any computer vision algorithm to achieve the 100% achievement in detecting the desired object, but till we are in the process to develop the algorithm so that it can detect near 100%. So why fuzzy is needed? Actually, fuzzy is needed because if we enlarge this image, so here the boundary is not certain, or there is some vagueness is present in this boundary of this solar coronal hole. So this cannot be detected using the other algorithm. Therefore, the fuzzy has been implemented for this case. So this is my overall work actually. And see here, one of the existing algorithm, active contour based model, doesn't detect the non-coronal hole region, which is actually present here. You can see some non-coronal hole region present, but it unable to detect using the existing algorithm. But the proposed algorithm has clearly detected this non-coronal hole region. So in next few days, I will work on this topic, on development of this AI-based computer vision algorithm for this coronal hole detection. And these are the team member who will, along with I will collaborate. So that's all. Thank you.
So I suppose all the teachers are done. So all of you must have been assigned one of the mentors. So if anyone is left, I think if anyone is missing, please let us know. Otherwise, if you have already been allocated a mentor, then after that we are going to have a tea break now. After that, you are going to contact your mentor, and then they will guide you how to handle the project in the next week. Yeah. You did not find your name anywhere? No, the person who presented will handle right? The Arpit has presented. So he will handle. Okay. All right then. Let's go for a tea break now if you don't have any other questions. Maybe you are supposed to attend the project. Your mentors are supposed to be here. If you are not present for the project, then we make a end of the
Okay.